Hello everyone and welcome to the channel. In this video, we'll connect an LCD to our computer and we'll take time to discuss some of the structure we need for the code, specifically calling conventions. I hope you enjoy. So in the past video, we've added this GPIO sheet, and specifically we've added to the circuit the 65C22 versatile interface adapter, which will give us GPIO and a number of other functionalities such as timers, a shift register, or interrupts. And in this video, I want to make use of our new GPIO port to connect an LCD module. First thing we need is to export the ports to the top level. There we go. Then I'm going to add a new hierarchical sheet to hold the LCD. So for the LCD, KiCad doesn't have the exact named module I want to use, but this one is close enough. It has identical pinouts and the right footprint. So this is the one I'm going to use. The module I'm going to use is based on the HD44780 controller, and that's the one that comes in Beniter's 6502 kit. So it needs power and ground. We also need to connect the power supply of the backlight to power. Then we have the contrast adjustment, and for that we can use a variable resistor between VCC and ground. And we can use, let's say, a 10K variable resistor. So now the question is, how am I going to connect those signals? And so we have two 8-bit ports that we can use from the 65C22. And some of the pins have special features, which I'm going to quickly add to the schematic here so we are aware of them. There we go. So CB1 can serve as the shift register clock and as the right handshake data taken pin. CB2 can serve as the shift register data, the right handshake data ready pin, and it can also serve as a output bit, so 1 or 0. In port B, pin number 6 can serve as the input to the second timer, and pin number 7 can serve as the output of the first timer. And then CA1 is the read-write handshake data taken pin, and CA2 is the read-write handshake data ready pin, as well as an output bit. So in order to connect the LCD, we need an 8-bit data bus and some control signals. If we look at these features, we see that PB6 and PB7 might be useful to keep free if we ever want to use timer 1 or timer 2. And so it makes sense to make port A the external data bus and put the control signals on port B and try to leave port number 6 and 7 free if we can. So for the display, port A is going to be the data bus. And then I will use PB0, run, and 2 to have the control signals. So we need to import those pins. And there we go. Okay, so this is our breadboard where we left off the last time. I'm going to add a new breadboard down here. And over here I'll put our LCD. So it needs power and ground. And we also need to power the backlight. For the contrast, I'm going to use this potentiometer. And I will connect it under the display. There we go. And now we're able to change the contrast. Awesome. So we need to connect port A to the data pins. And then we need to bring in the control signals. And so these are the 3 least significant bits of port B. And those connect in this way. So I need to find a way for those wires to not be in front of the camera, but also that we can see the LEDs that are here. So let's go and write some code for the display. So before we go and write some code for the LCD, I just have a little bug to fix. And somebody rightfully raised this issue in the comments, and it's something I went over really fast in the previous video. But here I want to initialize the stack pointer to 01FF, so the top of the first page. However, I'm doing this in native mode. And so the TXS instruction here, transfer X to the stack pointer, is going to copy the full 16-bit value of X, even though the registers are still 8 bits. And because we have loaded X with FF, the value at this moment is actually 00FF. And so this will initialize the stack pointer to the top of the 0 page, which we don't want. So I will just move this statement here. This way we initialize the stack pointer in emulation mode, and it will correctly go to 01FF. So now let's clear the test program. So we're not going to need this. We're going to focus only on the LCD. And because the LCD is 8 bits, I will work with 8-bit code for now. So we still have to configure the VIA. So I'm adding here a bunch of constants that we're going to use to configure the VIA. And that's just so we don't have arbitrary numbers laying around and we can read their purpose more easily. So I have here constants for configuring the peripheral control register, the interrupt register, and the pins of port A and port B. Port A, I've named them external, so that's the external data bus. And in port B, I've added which control line those represent. I've also added a default DDR setting. So for the external bus, by default, everything is going to be input. So we're not going to drive any signal on the external bus. And for DDR-B, only the pins connected to the LCD are currently going to be outputs. The other ones are going to be inputs. And remember, we don't have to worry about floating inputs on the VIA because the 65C22S has bus holding devices on its pins. And so if you don't drive the pins, they are not floating. So let me use this to initialize the VIA properly. And before setting the data direction register, we want to reset the ports to 0. And this works because the enabled signal of the LCD is active high. And so by writing 0 to the port, we are not activating the LCD. So now we are starting to write some actual proper code and just not some demos to demonstrate the hardware. And so I have to think about putting in some structure in how I write my assembly. And one thing that will really help give us some structure is calling conventions. And calling conventions are going to say when a piece of code is going to call another, they're going to define whether the caller or the callee needs to save, register, and restore it before returning. The conventions I've selected at the moment is that the A, B, X, and Y registers, and the C, N, V, Z, and B flags. So that's the accumulator, the hidden 8-bit part of the accumulator in 8-bit mode, the index registers, the carry flag, the negative flag, the overflow flag, the zero flag, and the break flag are caller saved. That means that when you call a subroutine, the subroutine may fully overwrite any of these, and it's the caller's responsibility to deal with it. And this means before calling a subroutine, if you know that you need to save the value in the A register, you need to do so before calling the subroutine because the subroutine is going to be able to overwrite this value. And the reason I'm doing it this way is that it's going to lead to cleaner code. And also the subroutine doesn't have to save all the registers it's going to be using if the caller doesn't need them. So the caller knows what data it needs and what it has to save. And so I think it's the better responsibility to have the caller saves the registers rather than the subroutine. Now, there are a number of things that are callee saved, and those are more about the configuration, I would say, of the CPU. And those are going to be the program counter, the stack, the direct page, the data bank register, the program bank register, as well as the decimal flag, the interrupt enable flag, whether the memory or the indexes are 8 or 16 bits, and the emulation flags are callee saved. So that means that if the subroutine, changes the configuration of the CPU, let's say it puts the CPU into 16-bit mode when it was 8-bit originally, it has to return the configuration of the CPU to the state it found it in before returning. And the callers can rely on this behavior. So in your code, if you call a subroutine, when that subroutine returns, you can expect that the CPU is going to be in the same mode as it was before. Now, the next two items are about the VIA. And because I'm using the VIA as kind of an external bus, there's 8-bit data bus and some control lines, we need to make sure that the control lines and the data bus stay consistent between invocations of various subroutines. And so the rules for port B, which is the control lines, is that a subroutine can only change bits in port B that are directly related to the hardware it is addressing. For example, an LCD subroutine can change the LCD bits, but must not change the state of the other bits. So if the caller code is doing something else with the VIA on port B, the subroutine can't mess with that. And finally, port A, which is the external bus, must be returned to input if it was set to output, and the port should be reset to 0 if it was used to output data. So this just means that the external bus is reset to 0 and disabled after a subroutine exits. Okay, so these are the first version of these rules. I'm sure I will be tweaking them as I go, but now I can be pretty confident when writing subroutines as to, what do I have to save and what can I overwrite in the subroutine or in the caller code. Okay, so I've written a LCD driver off camera. I'm not going to go into too much details on how this code works because Beniter already did a bunch of videos where he does that, and so I don't have to repeat those videos. So I suggest, if you haven't worked with this kind of LCD before, I suggest you go and watch Beniter's videos on his 6502 build. There you'll be able to learn how to address the LCD and make it display characters. Still, I will walk through the code that I've written and point out anything that could be interesting. Just as I did for the VIA, I started by creating a number of constants that represent the various values that you can pass to the LCD and the various commands. So we don't use, random numbers in our code and can use descriptive constants instead. And then I'm writing my subroutines. So remember from the calling conventions that my subroutines don't have to save any registers. So this cleans the code quite a bit. Here, I don't have to save the A register because if the caller needs it, it will have saved it. So in order to initialize the LCD, we have to clear the display. Then we configure it to 5.8.fonts. We set it that it's 2 lines and we use it in 8-bit mode. We turn on the blinking, we turn on the cursor, and we turn on the display. Then we set that the display is not moving with the cursor, and it's a left to right display, and then we return. So in our main initialization here, we have to jump subroutine LCD init. And of course, you have to include our library. And so this will initialize the LCD and turn on the display and the cursor and configure it. Now, this code uses the LCD instruction subroutine, which will send a command to the LCD, and it will take the command send in the A register. The first thing it needs to do is wait for the LCD to be available. So the LCD has a busy flag, and we have to check that the LCD is not busy before sending it commands. So this is what this does. And then we transfer the command into the X register. Then in order to satisfy my calling conventions, I have to first read the current control signals on port B and only modify those that I want. So we start by clearing all the bits of the LCD. We output the command to the external bus and we set it to output. And then we toggle the enable bit to send the instruction and we clear the external bus. And because always manipulated port B with AND and OR instructions that touch only the LCD bits, we can be sure that the other control signals haven't been touched here. and then we return. So this was a subroutine to send a command. I have another subroutine that's called print car, which prints a single character to the LCD. Similarly, it will take in A the character to print, and it will work identically. The only difference is that we are setting the register select bit in order to write characters. Then I have a subroutine to read from the address counter. This will be useful to get the position of the cursor on the LCD, and it will return the value of the current address in the A register. And it works similarly. The only thing we do at the end is that we only want the address, and we can strip the busy bit from the value that is returned. And finally, we have the LCD wait instruction, which is just waiting for the LCD busy flag to clear, and we call that every time we want to send data to the LCD. It will toggle the read-write in order to get the value of the busy flag. And as long as the busy flag is set, it will loop and keep executing this. And when the busy flag is not set, it will finish the subroutine and return. And so we can use it everywhere we want to send data to the LCD by just calling GSR LCD wait. Okay, so this was a quick overview of the code I've built to drive the LCD. Now let's do a demo. So I'll just print hello world. And once we've done, we can just stop the CPU. So let's try to assemble this. Of course, we have to use the immediate loads here as well, I guess. There we go. Let's try it out. Okay, let's start the CPU. There we go. Awesome. This worked on the first try. All right. So in this video, we've added an LCD to the computer, and we also took some time to put some structure into our code and discuss calling conventions. In the next video, we'll be adding 8 new GPIO pins to the Teensy monitor by soldering the optional header. And the first use I'll make of them is to rework some of the clock circuitry. So stay tuned for that. In the meantime, I hope you enjoyed this one. If you have any questions or feedback, let me know in the comments. And I hope to see you in the next one. Goodbye.